In the first two lessons, we were asking what would happen if we made charges build up but didn't let them go anywhere. Oh, they create a large electric field, like a planet with mass built up in one location. We said that although the Van de Graaff generator, we eventually let the charges arc, but initially we just saw that like charges unlike charges attracted. We didn't let them go anywhere. What we're going to look at for the remainder of this unit is what happens if we give the charges a pathway to travel, wires. We're going to build circuits. But first, we have to give you some terminology. And one of the terms we need to explain is the concept of voltage. What do we mean by volts? All of you have heard the term volts. Volts has a very, very specific and important meaning. So example one, part A, we're going to be looking at something called Ohm's law. Ohm's law is an equation. It's on your formula sheet, but in the same way that it was worth memorizing F equals what, MA, it's going to be worth memorizing Ohm's law because you're going to be using it on every question. But again, you're not going to need to make flashcards. You'll probably just memorize it on your own. Example one says, fill in the following key facts about voltage. First of all, what's the definition of voltage? Voltage is defined as the amount of potential energy per unit charge. The letter that we use as our abbrev for voltage is a V. There's a bit of a problem when we're handwriting. Is that voltage or velocity? Well, voltage is a capital V. Velocity is a lowercase v. Okay, Mr. Dueck, is that a capital V or a lowercase v? You write messy. I'm going to start doing a trick that I stole from my physics prof in university. Whenever he wrote this, that was lowercase v, to indicate that it was a capital V voltage, he often he put the little serif wings like on a type font, and so I often will do that. So you can write that down. Voltage is defined as the amount of potential energy per charge. That's an equation that I used to give people. It's one of the ones we crossed off the other day because I'm combining two units and shortening each one of them. But voltage is how much energy every coulomb of charge possesses. And so units, well, it's technically joules per coulomb. But this is so important, we give this a name. We call it volts. If something has 1 volt, what that means is every coulomb of charge passing through that object can give off 1 joule of potential energy, and you can do something with that energy. There's another word for voltage. Taya, I'm not wild about it, but it's used in the industry all the time. I don't like it because it's a bit confusing, but if you become an electrician or you become an electrical engineer, another word for voltage is the word potential. The problem is potential and potential energy are not the same thing, Marcus. And so there is potential, potentially, to confuse potential and potential energy. Potential energy is measured in joules. Potential is measured in It's voltage. In fact, you'll often, if you become an electrician, talk about a potential difference, a difference in voltage. And you'll say, current will only flow if there's a potential difference. If two objects are at the same voltage, the same potential, no current will flow. That's why birds don't get shocked when they land on a power line. Very rapidly, almost instantly, their bodies are raised to the same voltage potential as the wires. So we're going to start to talk about batteries. What happens inside a voltage source? Well, it all comes from the fact that like charges and opposite charges, everybody starts letter A? Okay. Inside a battery, a chemical reaction does work separating positives from negatives. Very similarly to the work I do when I lift something up from the earth. When I lift it up from the earth, I give it gravitational potential energy, mgh, Inside a battery, charges are separated. In fact, you can kind of think like voltage as being similar to height. The higher I lift something, the more potential energy it's going to have. The higher the voltage, the more energy per coulomb every charge will have. So inside a voltage source, work is done in separating charges. It's some kind of chemical reaction. There's all sorts of types, lithium, alkali, all sorts of types. I'm not going to get into those. But the chemical reaction that's going on there, in the same way as you give potential energy to an object when you lift it up, that chemical reaction is separating charges, giving them a voltage, an energy per coulomb, and you can kind of think of it as changing their height. Like charges, unlike charges, we prevent them from going towards each other inside the battery. Okay. In fact, typically what we do is we pretend that one end of the battery is positive, one end of the battery is negative. It's more complicated what's going on in the internal schematics of a battery, but we design batteries so that there's a negative terminal on what you would think of as the bottom and a positive terminal on what you would think of as the top. We don't write batteries when we're drawing circuits. We use symbols, and so the circuit symbol for a voltage source, it's a short line for the negative end, a long line parallel to it for the positive end. That's the circuit symbol for a battery. Technically, that's the circuit symbol for one cell. A battery is technically several cells in series with each other, so you might see something like that, but I'm lazy. We're going to do our usual, keep the math simple and lazy. If you see that, that's a voltage source, that's a battery. Because we can't see electrons, Eric, it's helpful to have an analogy. And the analogy that we're going to use is the concept of a ski hill. You're going to hear me time and time again say a change in voltage like a change in height. What a battery does is, in the same way a chairlift lifts skiers to the top of the mountain, giving them all potential energy, a battery lifts charges to the top of the voltage, giving them potential energy, electric potential energy. So the gravitational analogy of voltage, energy per charge, is height, which is energy per mass, and also there's a G in there, but we're going to pretend that's not part of it just to keep it simple. So here is a circuit. Here we have, for example, a 12-volt battery source. I'm going to say that's kind of, Ella, like a chairlift that lifts the charges 12 volts high. I know the measure of height is in meters, but I'm going to pretend that voltage is like a measure of height. How can these skiers get to the bottom of the chairlift? They have to get back down to ground level. So how many volts do you think we'll lose going through this resistor? If we're gaining 12 volts from the chairlift, how many volts must we lose going through that resistor? Be obvious. Yes. And so I'm going to treat the resistor like a ski hill. Now, technically, it's a 12-volt loss. It's negative 12. We don't bother putting the negative in. We all in the industry, we understand you lose voltage going through resistors. We're naturally lazy. We don't put the negative in front of it. We just say the word loss. So potential, or voltage, is like height. Positive charges want to fall downhill the same way a lifted object wants to roll down a hill. Let's talk about current. What happens if we connect a wire to one side of a voltage source? Well, like charges, I gotta be honest, a couple of electrons would move. But here's what would really happen. Very rapidly, the voltage of that wire, the energy per coulomb of that wire, would be the same voltage potential, the same energy per coulomb of the battery. It would like they would be on level ground. Charges would not flow. So really what we're going to say is nothing would happen. what if the wire forms a continuous loop? Well, now you would have electrons. In fact, we would say this: charges will flow. But I'm going to be a bit fussy. After you've written that, cross out the word charges. There is a word in circuits for the flow of charge. It also begins with the letter C, but we don't say charges. What word do we use to describe the flow of charge in a circuit? You've probably heard it. It's in the little mini title at the top of this page. Current. So cross out charges. We're going to call the flow of charge current. Current. In fact, for current to flow, you need a closed circuit. However, this particular circuit is terrible. Let's suppose this battery was a 24-volt battery. What that means is every charge, every coulomb, has 24 joules of energy to give away. And if you're leaving the battery and you're ending up back at the chairlift and you're ending up back at the bottom of the mountain, well, here in my analogy, we lost our voltage going through that resistor. You do have to lose all of your energy. Is there a resistor in this picture here? Okay, so the problem with this, all of the energy would go into heating up the wire. This wire would get very hot. It might even melt. Why is D a better circuit? Well, what did I make that earlier battery? 24 volts. If I have a 24-volt battery and I have to lose 24 volts, I'll lose my 24 volts, my 24 joules per coulomb in that battery. Did I go too fast, Aiden? You got it okay? All the charges would go into heating up the wire. Okay. This is a much better circuit. You're gaining 24 volts from the battery. You're losing it in the resistor. You don't have any energy left to heat up the wires. Now, in real life, the wires always pick up a tiny bit of heat, but Emily, we're going to pretend that they don't because it makes the math easier. Electrons need a completed circuit for current to flow. Put your pencils down, look up.
Ever held onto an electric fence? It hurts. Farmers use electric fences to keep cattle in and foxes out. If an animal touches the fence, it gets a shock and it runs away. Today, by holding on to this fence designed to shock horses, we're going to learn all about electricity.
Anybody here been shocked by an electric fence before? You have been? Okay. If you're on your phone, I would be tempted to shock you with an electric fence. I would never do that, but stay off your phone, please. Electric fences have a heck of a lot more kick than what we were getting from the Van de Graaff generator. Partly is because they have more charge to draw from. The nice thing about the Van de Graaff generator is whatever person is building up the charge, what's really happening is very quickly they arrive at the same voltage as the Van de Graaff. No more charge will flow on to them. So when you, Eric, were giving people shocks, I knew that only a small amount of charge is going to jump. Electric fence, much different.
This brainiac is going to touch the fence and get an electric shock.
Okay, got a shock. That must mean he's completing the current. So the electricity was going from the wire. Where was it going into? Be obvious. Where was its next path? From the wire into him. Then where? It's got to complete a circuit. So the electricity has eventually got to make its way back to this fence. So then where? Ground through his feet. Then where? Look, see these two very thin wires? Those are the wires plugged into those wires, back into the electric fence device, back up through the electric fence. There's the completed circuit.
This happens because when it touches the fence, it completes the circuit between the live wire. The charge goes from the fence itself into the brain, through the brainiac's body and down into the ground. Then it goes along the ground into the earth states, along the earth wires, on these polystyrene tiles. Brainiac?
What's our prediction if he touches the fence now? Is he going to get a shock or not? Why not? Current has to be able to complete a circuit. And because he's standing on an insulator, the charges cannot travel through his feet and get to the ground and get to those wires back there and get to this device. You can't complete a circuit, so he'll be fine.
Touch the fence. The electricity won't pass through the Brainiac's body because it can't go through the polystyrene tiles to the ground to complete the circuit because they're a good insulator, so no shock. Off the tiles. Shock. On the tiles. Shock. Off the tiles. Shock.
Okay. Next idea.
Every time this light flashes, there's a charge in the fence.
Electric fences are never on permanently. They pulse. If you had the electricity flowing all the time, your electric bill would be through the roof. And so you can adjust the pulse frequency once per second, once every 2 seconds, especially for cattle. From what you know of cows, are they swift moving, agile creatures? You'd probably get away with having a pulse every 4 or 5 seconds. So here, this one's got a pulse about every half second. What that means in theory is if you're holding the electric fence and you jump into the air while it's pulsing, you'll be okay because air is a pretty good insulator. In theory.
Now, if the Brainiac's feet aren't touching the ground when it flashes, he shouldn't get shocked. So if he can jump at the right moment, he'll be fine. Brainiac, are you ready? Excellent. On. Look at grab the fence, do when I say on, be in the air. Here you go. On. Do you have no sense of rhythm?
The theory is sound. The practice is much more difficult. You can't be off by even a little bit.
It's not difficult. You need to work on your timing. Or maybe we need to work on that theory a bit. Shocking a Brainiac. Shocking a whole load of them. In you go. All our Brainiacs are bare fit. Now, what will happen when the Brainiac at that end grabs the fence? It might just go straight through into the ground. It might make it all the way to here.
Why would there be some variation? Well, definitely some charges are going to go into the ground from the first guy. That's going to leave less coulombs, less current for the next person. Some charge will go through the next person, through the next person. There might not be any charge to reach the fifth person. Who knows? Let's find out.
Brainiac even feet. Who knows? Let's find out. Brainiac, on the count of three, grab the fence. 1, 2, 3. Find it again. We got that far. Go to this side. Take that outside. 1 to 5, how much did it hurt? 2. 1 to 5, how much did that hurt?
4 out of 5. That had some kick.
4. Right. Count order, and let's do it again. All right. 1, 2, 1. Didn't feel that. It seems that the current has never got past this Brainiac here. Who knows? There's only one way to find out. Stick him on the end. There we go. You go and grab the fence. My hat. Ready?
There's a lot of variation because each of these people would have different resistance, have different charge, ability to absorb charge. So there's lots of variation here. But they are completing a circuit if they're getting shocked.
As far as that Brainiac, it's Hey, what happens if we insulate these polystyrene tiles, all the Brainiacs along the line, apart from the one on the end? Maybe the current will make it all the way. Let's find out. Insulate yourselves, Brainiacs. Now, the first four in the line think that because they're insulated, you won't get a shock. No, not like that.
What's the prediction here? It's going to go all the way through because there is a completed circuit. Yeah. Even though four of them are on an insulator, they are part of a completed circuit. They're going to get a shock. Probably a pretty good one because they're going to absorb a lot of charge as a unit as well.
Because you were so for the first time, the camera went all the way to the very end, you all got a shock, and that looked quite severe. This because they were all holding hands, the current traveled in one line by the end, an insulated brainiac, giving everyone along the way a shock. I expect what happens if you're insulated as well. So, and unlike hands, grab the fence. 3, 2, 1.
So if all of them are on styrofoam, what's going to happen? Aiden.
Go. Well, look at that. That's amazing. Nothing because you're all insulated. That's very clever, brainiacs. I hope you've enjoyed learning about electricity. Well done. Good effort. That's what I say.
I wasn't going to say this, but I've looked around the room and I've recognized my audience. Playing with electricity and electric fences is dangerous. I'm sure they had ambulances stationed off screen. Don't go up to electric fences that you're unfamiliar with and start thinking that with some styrofoam and some friends holding hands, you can perform experiments with electricity. Don't do it. You heard them talking about electric current. Current is one of the 7 fundamental SI units. Here is how it's defined. The letter for current is a capital letter I. It's defined as the rate of flow of charge. It's defined as Q over T. And we've just turned the page. I think I gave you that one on your formula sheet in this. Yep. I think it's the next unit, electric circuits. Okay. Which, what would its units be? Well, it's technically a coulomb per second, but this is so important. We've called it an amp, named after a scientist whose last name was Ampere. Current is measured in amps, and the abbrev for amps is a capital letter A. What does damage, by the way, if you're getting shocked, is not the voltage, it's the current. The analogy I often give kids, because voltage is like height, if a single raindrop landed on your head from 5 kilometers up, that's high voltage, low current, very few charges. You wouldn't even notice it. If I dropped an entire swimming pool on your head from my ceiling height, that would be low voltage, but a lot of current. It's going to do some damage. Current was doing the damage. Again, the reason I was okay with letting you all get shocked if you wanted to from the Van de Graaff was I knew you were building up a very small Q, and even though it's getting you're getting rid of it in a quick time, the current wasn't going to be very big. Also, recall that the charge Q is a certain number of fundamental charges. Q equals NE. So we can relate current to the number of electrons that have moved through the circuit. I guess current equals the number of electrons times 1.6 times 10 to the negative 19 divided by time. I'm going to skip example 3 because I want to get to the punchline. Resistance and Ohm's law. Next page. So in our ski hill analogy, voltage was like the height. A chairlift battery increased the voltage, increased the height. You lost voltage going through a resistor. Resistors were like the ski hills. What's current? It's like the number of skiers. The flow of skiers up the mountain, the number of skiers on the chairlift, and down the mountain. And you know what? Because electrons flow at a constant speed in the circuit, we're going to pretend all the skiers go at the same speed. They use their skis to control their speed. There's a problem with this. In a circuit, it's electrons that flow. Electrons flow from negative to positive, because like charges repel and unlike charges, everybody starts with letter A, attract. But we would like to say that stuff flows downhill. In real life, electrons flow this way up the ski hill, and then they ride the chairlift down. That's the direction of electron flow. But we would like to say skiers go this way, and then they go down the hill. I think I told you Benjamin Franklin is the one who decided that electrons were negative. If we could, we would go back in time and say to him, you really should make protons negative and electrons positive. It would make a lot of the rest of the math around chemistry much, 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 much simpler. So here's what we're going to do. We're going to pretend. Aryan, we're going to define current as the direction positive charges would move in a circuit. Now, positives are protons. They're in the nucleus. Do protons ever leave the nucleus and start moving? But no. I'm going to argue, though, that an electron moving one molecule to the left mathematically is identical to the proton moving one molecule to the right, because they both have the same charge. So we would like to say that current flows downhill from a higher voltage to a lower voltage. So we're going to focus on the positive charges, the nuclei. The uphill flow of electrons mathematically is equivalent to the downhill flow of positive charges. So what we call current then is actually which way the positives would move if they could. Some textbooks, Emily, will call this conventional current because it is a convention. But here, let me show you this way. Example 4 says, draw the direction of electron flow. If this is a circuit, the longer bar of the battery is the positive end. Electrons would flow this way. But that would have them skiing backwards up the ski hill and then riding the chairlift back down to the bottom of the mountain, which is confusing. Current is that way. And I'm going to use my capital letter I as the abbrev for current. I like that question. I like that question. I like that. So in my ski hill chairlift analogy, current would go this way. Electrons, I'll change colors for electrons. You know what? I'll do the electrons on the other hill. Electrons would go that way, which is just yucky and confusing. So for the rest of this unit, we'll talk about conventional current or current as always flowing from a higher voltage, Victor, to a lower voltage, even though an electrician would say, no, the electrons are going from the lower voltage to a higher voltage. Yeah, I know. This is also why a good word for voltage is potential. What we say then is charges flow from a high potential to a low potential, from a higher voltage to a lower voltage. Soccer? Yep. Good luck. Let's talk about resistance. Every circuit offers some resistance. Our abbrev for resistance is a capital R if it's a big resistance. Sometimes if it's meant to be a tiny resistance, we'll use a lowercase r. I know lowercase r is also radius. Victor, I think I've mentioned once or twice, we don't have enough letters in the English alphabet. We're having to reuse. There's a circuit symbol for resistance, and I wrote here, which you should recognize from Science 9, but I recognize many of you had your Science 9, Science 10 interrupted by COVID, and so you may not have seen this, so I will be teaching this from scratch. The circuitry symbol for a resistor is just a series of wavy lines like that. And you will need to know these symbols, but you'll memorize them because I'll throw so many of them at you, so don't worry about making flashcards or anything like that. Where does resistance come from? Well, it kind of comes from electric friction. The electrons that are moving through the wires, they bump into the atoms of the material they are passing through. And in the same way as when you rub your hands together, it generates heat, the electrons traveling through, they lose some energy, some voltage per some energy per coulomb, some voltage as heat. And we're very clever at turning that heat into useful stuff. So a loss of energy implies a loss of voltage or a voltage drop. If you have a circuit. First of all, what direction is the current flowing according to the circuit? To the left or to the right? Be obvious here. To the right. What direction is the electron flow? To the left, but we're going to pretend from now on it's current. Okay, let's suppose you had a voltmeter, and right here you measured 8 volts, and then here you measured 3 volts. Fahim, how many volts did you lose going through the resistor? Be obvious. Yeah, and you could write -5, but because we know resistors are always a voltage drop, we're lazy. We don't label it with a negative. You lost voltage. What that means is every coulomb of charge that goes through there gives up 5 joules of energy, 5 joules per coulomb. And we can use that energy to whatever. Depends on the device. The amount of flow current through a circuit depends on the total amount of resistance and on the voltage applied. We're going to do a little thought experiment and see if we can derive Ohm's law just from common sense. So it says, what can be said about the current flow in each case? Fill in either large current flow or small current flow. High resistance. High resistance means it's tough to get through. You know what? Think a ski hill that's a narrow trail. Can you get more skiers or less skiers on that narrow trail? Will you have a higher current or a lower current with a high resistance? Can you get more skiers or less skiers on a narrow trail? Will you have a higher current or a lower current with a high resistance? Okay, so as resistance increases, current decreases. What about a low resistance? Now I think you have to go for, okay, that's right. Good luck. I think of low resistance. Ski hill, it's like a kilometer wide. Can you fit more skiers, current, or less skiers? Yeah. So as R decreases, I increases. You know what that means? In terms of an equation, if we're relating I and R must be on the bottom, because when it gets bigger, I get smaller, right? What about voltage? Voltage, what did I say voltage was similar to? Starts with letter H. Height. What's more popular, a tall ski run or a bunny hill? Be obvious. Tall ski run. So as voltage gets bigger, current gets bigger. As voltage gets smaller, current gets smaller. Those ones match, so the V is going to be on the top. That's Ohm's law. I equals V over R. It says in a word, write a word equation. I'm not going to write a word equation. I'm going to write a mathematical equation. So you can write I equals V over R, but it's never written that way. It's always written as V equals I times R. This one is on your formula sheet. This one you want to memorize. You will memorize it. V equals I times R. How many of you have seen that one before in Science 9 or Science 10? Okay. I know I always did electricity. You may have noticed I like electricity. It's, I can shock you and things, but also it's just, it surrounds our lives. You should have a rudimentary understanding of how it works. It shouldn't be witchcraft and magic. Technical comment. Technically, if I go back to my ski hill analogy, you're either gaining or losing voltage. Voltage is always a change in. And so don't write this down. Technically, there should be a delta there, but in the same way time is always a change in, we get lazy and we stop putting the delta in front of it a long time ago and we do whatever. Okay. But you should read that V as a voltage drop or a voltage gain. It's really a change in voltage. Or in the industry, they'll talk about a potential difference. The units of resistance are ohms. So current is measured in amps. Voltage is measured in volts. That's the easy one. Resistance is in ohms. Why wouldn't I use a letter O as my abbrev for ohms? Why would that be a bad idea? Looks like a 0. So we use a Greek letter O, and omega. That's that little symbol right there. 1 ohm is 1 volt per amp. I just got the R by itself from V equals I times R. Good conductors have low resistance. Poor conductors or insulators have high resistance. Example 6, this is not on your test, but since I'm introducing a new concept to you, I always like to give you an idea of what's really big, what's really small. Fahim, what I did here is I wrote 6 objects, and then I took their resistances and I scrambled them. So don't just read across. Look at these 6 objects. Based on your knowledge of electricity, which of those do you think is the best insulator? And in fact, we use it as an insulator. Which of those do you think conducts electricity the worst? Nicole, make a guess. Yes. What's the highest resistance over on the right? Glass basically has a nearly infinite resistor. Let's cross that out. Yeah. On the power lines, the big metal ones, the ones that run over the mountains, if you look where the wires come in contact with the metal scaffold, those black things, that's like black ceramic glass. Otherwise, you'd be sending the electricity through that metal into the ground. It would not be good, right? Let's reverse this. Of the remaining 5, which of these do you think has the least resistance? In fact, near zero. In fact, we're going to pretend it's 0 to make our math easier. Which of these, Joanna, do you think has the least amount of resistance? Yeah, zero 0.1 ohms. We're going to pretend it's 0 ohms to make our life easy. What kind of wire, by the way? Copper. You can also, silver is even better, lower resistance. Gold is even better. Why don't we use silver or gold? Okay. But if you ever see a NASA probe on the ground, look, there's a lot of gold on it. NASA is willing to spend the money for the more expensive wiring because every 1/10 of a watt that they can save, that means that probe is going to last longer. Or if it's using solar power from Mars, that means the solar cells can be a tiny bit smaller or whatever. The solar panels can be a little smaller or whatever. So NASA, their wiring is almost always going to be the expensive stuff. Okay, let's go back to the next one. The biggest resistance is remaining us. We're pretty good insulators. What's the biggest number that's left, Dean? Yeah, human beings, it varies, depends how sweaty you are. Honestly, depends what part of your body, but anywhere from tens or hundreds of thousands of ohms. This is why I've said to you, you get shocked all the time and don't realize it. It doesn't penetrate your nervous system, so you just don't notice it. Uh, Electric motor is 5 ohms because the higher the resistance, the more you'll heat up. We don't want electric motors to heat up, so they're typically very low resistance. And then the last 2, I happen to know an average lab resistor is around 2,200 ohms, and a light bulb is about 200 ohms. The incandescent light bulbs, not the LEDs. LEDs are very different. I'll probably have to change this in about 4 years because kids won't know what those incandescent bulbs are like anymore. By then, probably most people will have moved to LEDs. Again, technical comment. R changes as the object heats up, as the wires heat up, the resistance changes. Kyle, we're going to pretend that's not happening. Much like we ignored air resistance, we're going to make our lives easy. R is constant. Okay. Let's talk about how humans get shocked. So although human skin is a good insulator, typically in the tens or hundreds of thousands of ohms, it will only protect us to a certain point. Air is a good insulator, but if you have a high enough voltage, lightning can occur. The air will act like a wire. It will ionize, passing an electron to the next air molecule, 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 to the ground. You have to have a big voltage. Human skin can do the same thing. And once the electricity has passed beyond our skin, on the inside, we're mostly salty water. How's salty water as a conductor? Pretty good. So what happens when humans get shocked? There are 2 dangers. The first is heating up of tissue as electricity flows. That's why people often get badly burned when they get shocked. So I didn't tell you the story of my uncle a couple of days ago who almost died, right? I think I only did it with 1 block. My uncle, we used to, on my mom's side, My mom's last name is Jesse. Hey, now you can hack into a bunch of security. No, because I never used my mom's maiden name as a security code. That's so stupid. Jesse Farms used to be the largest privately owned raspberry plant in BC. They ended up going bankrupt about 10 years ago. But for 40 years, half the kids in Abbotsford worked at Jesse Farms as their summer job. My uncle, Will Jesse, was one of the people that worked there. They had a massive cooler, and whether it's a heater or a cooler, if you're moving temperature around, what you're really doing is you're moving heat around. What you're really doing is you're moving electrons around. You got a big current. That's what you have. The cooler was the size of our gym, maybe even a little larger. And he was testing out the cooling mechanism with a voltmeter, and he didn't realize the voltmeter was faulty. It had a short circuit. So he ended up probably putting a couple hundred amps through him. Okay? Blew the breaker, the lights went off, and he's told me because he was in an enclosed room with no windows and no doors, he thought he'd gone blind. He says, I remember sitting there just thinking, my God, how will I provide for my family? I'm blind. And he said, I started feeling found a wall, crawling, and then I said, I think I know where the door is. I started crawling, trying to find my way to the door. He opened the door. He says, boy, when I saw daylight and realized that I couldn't see because it was pitch black because I'd blown the breaker, not because I couldn't see, so I almost started crying with relief. Meanwhile, my cousin was working in an office across the parking lot, and the lights had flickered weirdly. And that kind of made her, that's odd. And so she had kind of poked her head out of the window just in time to see my uncle flop out. He survived, but he still has burn scars all over his body. But he survived 100%. Okay? Don't muck around with electricity. So that's one danger. There's a second danger as well. The flow of electricity through the body can disrupt your own electric nerve impulses because your muscles work on electricity. And when those muscles are your heart and your diaphragm, pumping blood and breathing, that's not a good thing. To shock you and burn you needs a fairly high current, but to get your muscles to twitch, or fibrillate is the fancy word, you only need about 100 milliamps, 0.1 of an amp, nicknamed the death current. If such a current flows through the heart can stop or twitch helplessly. So 100 milliamps, 0.1 amps is not very big, hence my be careful when dealing with electricity. Don't do it if you don't know what you're doing. In my ski hill analogy, resistors act like ski slopes that connect the top of the hill to the bottom. They're the ski hills. The amount of resistance or electric friction, you can think of it in two ways. You can think of it maybe as how deep the snow is. If it's really deep, you can't go very fast. I think of it as how narrow the trails are. High resistance, narrow trail. You'll get a few skiers, small current. Low resistance, wider trail. You get a bunch of skiers on there. Ohm's law for ski hills states that the flow of skiers varies directly with the height of the mountain and inversely with the depth of the snow. Stay what? Flow of skiers is current. It varies directly with the height of the mountain. To remind me to upload the lesson. And indirectly with resistance. Except we got the V by itself. How would I get the V by itself? How would I move the R over? What's on your formula sheet? Everyone memorizes Ohm's law is V equals I times R. That's just an easier form to memorize it in. Okay. Example 7. Arian, what does example 7 want me to find? Current. Okay. Well, we have Ohm's law, V equals I times R. Arian, get the I by itself. How do I move the R over? Yep. In this first circuit, now we should point out, here's what's really happening. How big is the battery? How many volts is the battery, Arian? What we're saying is every charge gains 6 joules, 6 volts per charge, and then you're going to lose all 6 volts going through here. So label the motor with 6 volts. How many volts are we losing in the motor, Arian? What's the resistance of the motor? How many amps are flowing through this circuit? What's a clever way to divide by 25? Times by 100 and divide by 4. 0.24? Units, current. I know it's new. I'm not mad. What are the units for current? Anybody? Amps. Okay. You will have to memorize that, but you will. Now, this next one, this is a short circuit. Same battery, but all I'm doing is connecting one end of the battery to another end of the battery with a near zero resistance wire. Eric, let's run the numbers. I equals V over R. Eric, how many volts do we have to lose in the battery itself? Gotta lose 6, because we were able to start 6 volts high and end up at the bottom of the chairlift 0 volts high. So we gotta lose 6. What's the resistance? How many amps? This is going to start heating up red hot and probably melt the wires. Now, 2 other things as well. Remember, current is also the amount of charge per second. This will drain the battery wicked fast. You're pulling thousands of coulombs out per second. This battery might last a minute before you've drained it. That's why you don't do this to batteries. It's hard on batteries. Where this one here, pulling out 0.24 coulombs per second, you might get 30 or 40 minutes before you drain this battery or more. So short circuits are bad. I wrote here, technical comment, the second diagram is an example of what we call a short circuit. It's called short because there's very small resistance between either end of the chairlift battery, between the ends of the terminals of the battery. And so it will experience very large currents. Now, if you short circuit one of these, meh, you'll just wreck the battery pretty quickly, but meh. You short circuit a car battery, that has enough charge stored into it, you can melt the wires. They'll certainly get red hot, but you can melt the wires. If you short circuit the power coming out of there, the problem with a power outlet is that has unlimited charge, because BC Hydro will keep feeding coulombs as long as the circuit is complete. And so that's not good. That's not good. Your stove elements and your oven element, if it's an electric stove and if it's electric oven, that's a controlled, deliberate short circuit. That's done on purpose. Also, you might notice if you ever pull your stove off of the wall, it's a different outlet. It's a special outlet because it's handling more than your standard amount of current. We'll talk about that, I think, in the next lesson. Okay. So far, I've been talking about DC direct current flowing in one direction. What comes out of our outlets is AC, alternating current that goes this way, then this way, then this way, then this way. In fact, it goes back and forth at 60 hertz, so it switches direction 120 times a second, or it makes one full back and forth 60 times a second. It has a voltage amplitude of 110 volts. It's actually, I think it's 113.4. We usually just say 120 because we round off. Everything that I teach you for direct current works for alternating current, but we'll talk about why it's alternating current a couple of units from now. What's your homework? Number 1 is good. 2 is good. You can skip 3. 5 is good. 6 is good. 7 is good. We'll pause there. I know a lot of you also have homework from the last 2 lessons.